Okay, so the first two lectures were about material from the 60s and 70s, and the third lecture was about material from the early 2000s, so now we're finally going to get to today. But before getting to today, I need to hop back to the 60s and 70s for a second. So the subject of today's lecture is analyticity and spin. The starting point is an interesting kinematic situation that one can access in Lorentzian signature, but not in Euclidean signature. And that's the Regge limit. So the Regge limit is obtained by, let's take a 4-point function. And we can start with the 4 operators space-like. And we take 2 of them and we boost them relative to the other 2. So this is one way of drawing the picture. And my labeling for the operators will be like this. We could, if we like, boost them a bit more democratically. So another way of drawing the picture would be, so here's Minkowski space. And let me pick 2 crossing null planes in Minkowski space. And then we have operator 2 up here, operator 3 down here, operator 1 here, and 4 here. And they're approaching these null planes. This. Okay, so this is just equivalent to this picture under an overall boost. And so the Regge limit is a CFT version of a high energy scattering process. So the idea is that these operators 1 and 3 create excitations. The excitations propagate up and they interact somehow in the middle of Minkowski space, and then they're detected by 4 and 2. And in the Regge limit of extremely large boosts, the interactions happen at very high energies. Okay, so there's an important and pretty non-trivial fact that 4-point functions are bounded in the Regge limit. To explain this, first let me explain why it's non-trivial. So why you might not expect them to be bounded, and then I'll explain why they're bounded. Let's look at a 4-point function. We have some conformal block decomposition. And actually, the important ordering for us is going to be 4, 1, 2, 3. I'll explain that in a little bit. Okay, so we're going to look at this 4-point function. And this thing has a conformal block decomposition, so it's a sum over operators. Oh, let me write it like this. So g of z and z bar over x12 to the 2 delta phi, x34 to the 2 delta phi, where this function g of z and z bar has an expansion in conformal blocks. It's a sum over operators O in the phi phi OPE with OP coefficients squared times a conformal block. The conformal block depends on the dimension delta of O and the spin j of O and 2 cross ratios. So we can use conformal transformations to put all 4 operators on a 2-dimensional plane. Then I'm going to use light cone coordinates in this plane. So this is the v direction. This is the u direction. So v is t plus x. U is t minus x. And these cross ratios, after I put the 4 operators on the plane, these cross ratios can just be written in terms of the u and v coordinates of the operators. Okay, so So z is u12, u34 over u13, u24, and z bar is the same thing with v's. Okay, so good. So let's so if we start in this kinematics where all four operators are space-like separated, then and in fact we can, if we like, just start with them on the t equals 0 slice. Then you can check for yourself that z and z bar are both real and between 0 and 1. And now when we move from this configuration, we start moving 2 this way and 1 this way, we're going to encounter some kind of branch cut when 2 becomes light-like from 3 and 1 becomes light-like from 4. And the way we move around the branch cut depends on which Whiteman function we're looking at. So it depends on our I epsilon prescription. So let's try to sort that out. Or at least I'll get you started on sorting that out. So let's look at this ordering that we have here. And I'm often going to use the abbreviation where phi sub I means phi of x sub I. So in most of this lecture, I'm just going to consider one scalar operator, phi. And so these are not different operators. They're operators at the position x phi. Okay? So this is just useful shorthand for now. Okay, so how are we supposed to access this Whiteman function? Well, what we need to do is shift the imaginary parts of the times so that the Euclidean times of these operators are in order. So in particular, we need to take, say, t23 and give it a small imaginary part. This ensures that t2 is later in phi 2 is later in Euclidean time than phi 3. And similarly, we have to do that for t41. And we actually don't have to bother with any of the other differences of times. And the reason is that in the kinematics we're considering, all other pairs of operators are space-like separated. So we're never going to encounter branch cuts associated with those pairs of operators. And so we don't have to worry about that. But of course, there is a unique way to assign an ordering to the Euclidean times. But I'm just going to, it suffices to just write this formula. And then the other comment is that when we move into this kinematics, if we're just interested in understanding what happens to the cross ratios, nothing particularly interesting is going to happen to the cross ratio z. And the reason is that we can keep the u coordinates of all the operators fixed if we like, and just move 1 and 2 along lines of constant u. They're never going to encounter branch cuts in the u coordinates. The branch cuts are just going to be in the v coordinates. Okay? So nothing interesting is going to happen to the z cross ratio. Instead, the only interesting things are going to happen to the z bar cross ratio. So that means we'll keep the ui's fixed. And as a consequence, I can rewrite these shifts in terms of v's. Okay? So what we really need to do, if we're keeping the u's fixed, that means we need to shift the v's like this. Okay? So the idea is to make these shifts and then start moving the operators into this new kinematic regime and see what happens to this cross ratio, z bar. Okay? And I'm going to leave that as an exercise, and it's one that I really encourage you to do. And I'll give you what the result should be. So first of all, for this correlator that we're looking at, let me write it in terms of something that's just a function of cross ratios. Okay, so the claim is that if you keep track of what happens to the z-bar cross ratio, then this is what you'll get when you move into Reggie kinematics, where the meaning of this is to move z-bar around 1 in the indicated direction. So the claim is that in cross ratio space, what happens, so here's 0 and here's 1, we start with z and z bar both real in between 0 and 1, and when we move into Lorentzian kinematics, when we move into Reggie kinematics, z will just stay between 0 and 1, and nothing much interesting will happen to it. When we go to the Reggie regime, z is actually going to move towards 0, and we'll explain that in a second. But z bar initially goes around 1 like this, and then we'll start coming back to 0. Okay? And the way in which it goes around 1 is dictated by this I-epsilon prescription, as you should check for yourself. Okay? And so you can do this exercise for other Whiteman correlators. So for example, phi4, phi1, phi3, phi2. And it turns out in this case, there's no monodromy on z bar. So this case differs by swapping the order of 2 and 3. We can also swap the order of 1 and 4. In this case, there's also no monodromy on z bar. And then finally, we can swap the order of both. And this gives a monodromy on z bar the other direction. Okay?
These are all multiplied by those x.
That's right, yeah. They all have the same prefactors here. Okay? So the fact that there's no monodromy in this situation can actually be understood in terms of an old result due to Mach. In particular, let's look at this example. So the operators 1 and 3 are space-like separated from each other. So I can swap them if I like. So this is the same as phi4, phi3, phi1, phi2. There's an old result due to Mach that the operator product expansion always converges if the two operators are acting on the vacuum. So that means that Mach's result implies that we should always be able to do the operator product expansion between 1 and 2 in this Whiteman correlator, because I can move 1 so it's next to 2 and they both act on the vacuum. The regime of OP convergence, maybe Slava talked about this, maybe he didn't, but the regime of OP convergence is that the OPE converges as long as the cross ratios stay away from a cut from 1 to infinity. Okay, so if z and z bar, this is just another copy of the same picture. If z and z bar range around in the complex plane but never touch the cut, then the OPE will remain convergent. Okay, and so the claim is that Mach's result tells you that you should expect the OPE to be convergent in these two cases. And indeed, when you check what happens to the cross ratios, that's what you'll find. You'll find that the cross ratios never pass through the cut in those cases. Okay, good. So this is what the I-epsilon prescription tells you happens to the z-bar cross ratio. And then finally, I want to explain why both cross ratios eventually go to 0 in the Reggie limit. So one way to see this, the simplest way to see this, is to just imagine performing this boost. Okay, so after we boost, let's say let's say that we started with the operators let's say this distance was r, and this distance here was 1. So then in light cone coordinates, we could boost 1 and 2, and we would have something like, so 1 is diametrically opposite from 2, so minus u1 is equal to u2. Similarly for v, and these would be equal to minus e to the minus eta r, e to the eta r, where eta is a boost parameter going to infinity. Okay? So what's happening here is that when eta gets big, the v coordinates of these operators are getting big, and the u coordinates of the operators are getting small because they're getting pushed towards this light cone. Okay? And so you can just plug this in to these formulas and verify for yourself that z and z bar are going to 0 in the limit of large eta. Okay? But there's another cute way to see why that's what's happening to the cross ratios that I like a lot, because I don't like having to do calculations. I prefer drawing pictures. So the idea is, so let me draw again the Reggie limit. Let's see. Okay, so the cute idea is that the cross ratios depend only on the Minkowski coordinates of the points. So in particular, they're unchanged if we apply this T operation. So this T operation was the one where you start with a point, you send light rays in all directions, and you find where they converge on the next point gray patch. The point that you get with the T operation has the same Minkowski coordinates as the original point. It's just in a different patch. So what that means is we're allowed to move these points to their cousin points in other patches, and we'll get the same cross ratios. And here's what we should do. We should move this one to, we should, instead of looking at this one, we should look at its cousin, which I'll call 2 minus. In this lower point gray patch, and similarly for this guy we should look at 4 minus in the other also in this lower point gray patch. And in the Reggie limit we have these operators approaching the null planes, but that translates to this picture here. And so you can see that in terms of 1 and 2 minus and 3 and 4 minus, the Reggie limit kind of looks like an OPE limit. Okay? Now, this is just a statement about cross ratios. The cross ratios are doing the same thing as in the OPE limit, but of course the physics could be very different. The physics will be different if we're in a situation where we have some monodromy that happens on the cross ratios first. Okay? Okay, so this is how to see that the cross ratios go to 0 without calculating anything. Okay. Good. So in particular, this implies that in the cases where there's no monodromy, so for example, phi 4, phi 1, phi 3, phi 2, so this thing is just equal to g of z and z bar, and in the Reggie limit, we just get to pick out the leading term in the small z, z bar expansion of this thing, which is just coming from the unit operator. So this is 1 plus ... in the Reggie limit. Okay? So for this particular Whiteman 4-point function, we've seen how it behaves in the Reggie limit, and it's pretty simple. But something much more complicated happens for the other Whiteman functions. So for example, the one that I mentioned before as being interesting. So in this case, so in all these cases, I'm multiplying by this dimensionful factor to make it dimensionless. So we have this. And one thing we might try is to perform this monodromy term by term in the conformal block decomposition. Now, I already warned you that that's not going to work because I said that the regime of convergence of the conformal block decomposition was the complement of this cut, and the monodromy is going to force us to go through the cut. But let's just see what happens. So what we could do is take a conformal block, G delta J, and perform this monodromy on it. And what do you get? So the conformal blocks are solutions to the conformal Casimir equation. And the conformal Casimir equation has, it's a second order partial differential equation in two variables. It has 8 different solutions. It turns out to have 8 different solutions. And when you do some monodromy, you start out with one solution, you'll end up with a linear combination of the 8 possible solutions. It turns out that the linear combination that you get in this case is, so there's one piece proportional to the original thing you started with. And then you get another term proportional to G 1 minus J 1 minus delta. These quantum numbers should be familiar to you by now. These are the same quantum numbers that appear in the light transform. And hopefully I'll have time to explain the significance of that. Okay, so you get this other term. This is then a big problem if you want to try to do the monodromy term by term in the conformal block decomposition. The problem is that, so these conformal blocks, so normally G delta J of Z Z bar behaves as Z Z bar to the delta over 2 times higher order terms in Z and Z bar. So that means that when we do these, when we have these light transform quantum numbers, we get something like Z Z bar to the 1 minus J over 2. If we do this boost, then it turns out that both Z and Z bar, as you should calculate here, go like e to the minus eta in the limit of large boost. So this gives us e to the j minus 1 times eta. So we get a badly divergent series when we sum over spins. Okay, so high spins give growing contributions, and that you could just guess from this picture already. The idea is that the spin gives the boost eigenvalue of operators in the 1,2 OPE. And we're boosting a lot. So obviously the operators with a high boost eigenvalue will contribute more and more and more. And this funny exercise with taking monodromies of conformal blocks tells us that instead of getting e to the j times eta, we get e to the j minus 1 times eta. And the shift from j to j minus 1 has to do with the fact that the conformal blocks sum an infinite set of descendant operators, and that sum modifies slightly the behavior in the large boost limit. Okay, but the intuition is just e to the j times eta, and of course it's blowing up. Okay, so that's why you might be a bit worried about the Reggie limit. But again, it turns out that the 4-point function is bounded in the Reggie limit. So let me explain why that's true. In this particular case, for a 4-point function of identical operators, one way to explain boundedness in the Reggie limit is to do the OPE decomposition in a different channel. So we do the OPE decomposition in a different channel and observe that when you go to the Reggie limit, you just insert some extra phases into the OPE decomposition, and it doesn't make it any bigger. But there's a more general way to argue this, and in fact, you need the more general way to argue it if you want to talk about correlators of non-identical operators or spinning operators. Okay, so I want to explain the more general way because I'd like to give you guys some tools to work with in the future. So the more general reason is something called Rindler positivity, which I unfortunately won't have time to prove, but at least I'll give you the statement of it and show you how why it implies Reggie boundedness. The idea is that any quantum field theory has an anti-unitary symmetry, CRT. So usually you hear about CPT, but CRT is the correct anti-unitary symmetry. CPT is the wrong one. So CRT is an anti-unitary symmetry that squares to 1. It acts by reflecting one time direction and one space direction. So if we have a point t, x1, x2, ... xd minus 1, and we act with CRT, it gets mapped to a point that I'll call x bar, which just has minus t, minus x1, and then all the other coordinates the same. And I'll define the Rindler conjugate of an operator O by just conjugating by CRT. In particular, for traceless symmetric tensor operators, we can, so here I'm using index-free notation. The Rindler conjugate of the traceless symmetric tensor operator is just given by the Hermitian conjugate operator at the position, at the Rindler reflected position and with the Rindler reflected polarization vector. Okay. And one comment I should make is that Rindler conjugation preserves operator ordering. So it's not the same thing as Hermitian conjugation. So the Rindler conjugate of AV is the Rindler conjugate of A times the Rindler conjugate of B, and that just follows from the definition. Okay, so the definition just involves inserting this CRT operator, which doesn't reverse the orders of anything. Okay, and CRT squares to 1, so you can just evaluate, just plug in the definition here and verify for yourself that it's equal to this. Okay, so the statement of Rindler positivity is that if you have a collection of operators localized in the right Rindler wedge, and I'll call this product of operators A, then we can take its reflection, and maybe I drew too complicated a picture to allow myself to take the reflection here. So, oh gosh, I don't even know what I'm doing. Okay, so this would be the reflection. And the claim is that the expectation value, this expectation value is positive. Okay, and this is true whenever A is the product of operators localized in the right Rindler wedge. I think that maybe the cleanest way to argue for this uses Tomita Takasaki theory. Did Tom Faulkner talk about that at all? He did. Great. Okay. So exercise, look at Tom Faulkner's notes and try to prove this for yourself. Okay. So positivity of this thing means that we can define a positive definite Hermitian inner product by just this expression. So I've defined an inner product B with A as omega B bar A. And because this is positive definite Hermitian inner product, it satisfies a Cauchy-Schwarz inequality. So, okay, so let's return to our 4-point function. And let's choose the points to be in a Rindler symmetric configuration. So let's see. So we have 3 and 4 and 2 and 1. And with these choices, we have, for example, that phi 1 is phi 2 bar, phi 4 is phi 3 bar. Okay, and importantly, we can choose a Rindler symmetric configuration without restricting the types of cross ratios we can talk about. Okay, so this staying within Rindler symmetric configurations, we still have 2 degrees of freedom. So I can move the point 2 around wherever I want, and just move 1 in a reflected way. And so 2 degrees of freedom maps to 2 cross ratios. Okay, so we're not restricting the cross ratios at all. so we're free to choose this. And so then we can apply the Cauchy-Schwarz inequality. And the cool thing is that because Rindler conjugation doesn't change operator ordering, it will give us relations between different Whiteman orderings. So let me do an example. So the Cauchy-Schwarz inequality implies that phi 4, phi 1, phi 2, phi 3 squared. So this is just our inner product. And in our Rindler symmetric configuration, I can replace phi 4, phi 1 with, so this is just the bar of phi 3, phi 2. So this is this inner product. And by Cauchy-Schwarz, this is less than or equal to phi 2, phi 3, phi 2, phi 3, phi 3, phi 2, phi 3, phi 2. And this is just a product of the nicely behaved Whiteman functions, phi 1, phi 4, phi 2, phi 3, i.e. the ones that don't experience any monodromy when you go into the Regge regime. So in particular, we find that the absolute value of this analytically continued G is less than or equal to the non-analytically continued G squared. So, and by the way, I should mention that this computation right here is one that you've seen already in this TASI, except it's in disguise. So this is the same, essentially the same, or it's a special case of the Cauchy-Schwarz argument that goes into the proof of the chaos bound. So in the proof of the chaos bound, there's a centrally important step where you use Cauchy-Schwarz to relate two different thermal correlators to each other. And the interpretation here is that one can try to quantize your quantum field theory in Rindler space. And the Rindler time is exactly this boost parameter. And so the Whiteman functions that we're looking at can be interpreted as thermal correlators in Rindler space, and then exactly the Cauchy-Schwarz argument that goes into the chaos bound becomes this argument. But that's the way of thinking of things is unfortunately a little bit schematic because we don't really know how to make sense of Rindler quantization in a general quantum field theory. It probably makes sense. Maybe it makes sense, but there are some issues if you think about what happens near the origin. So near the origin in Rindler quantization, you have to, if you want to quantize the theory on a half space, you have to say what happens here. And in particular, it seems like you need to put some kind of boundary condition there. And I would say that the question of what boundary condition you should put there is not totally understood. You can do replica trick computations where the need to specify a boundary condition goes away when you take the n goes to one limit. And so there's a sort of, there's a story there. It's not clear how rigorous a footing it's on. So this, I would say that it's the relation to Rindler quantization, if you really want to work rigorously in quantum field theory, is at this point an analogy. But Tomita-Takasaki theory gives a rigorous way of saying that this is a positive definite inner product, and that's sufficient for what we're doing. Okay, so we have a conformal block decomposition that is naively becoming divergent, but magically the correct answer is not divergent, it's bounded. So what's going on? And for this, it's useful to think about a toy model. And so this toy model is, we're going to consider an amplitude So amplitude is in quotes. So it's just a function of a single complex variable. And let's suppose that it has a partial wave expansion. So this will be a sum over spins of some coefficients times w to the j. And you should think of w as being e to the eta, where eta is a boost parameter. And let's make a few assumptions about the properties of this amplitude. So first of all, we're going to assume that it's analytic everywhere outside a cut starting at w equals 1. And second of all, we'll assume that it's bounded in the Reggie limit, by which I mean, let's see it. Yeah, so this is less than or equal to 1 as w goes to infinity. Okay, so this toy model exhibits this sort of mystery that we're dealing with here. The idea is, how is it possible that you could sum up something where every term is growing and yet the final result is bounded? Well, if we're just thinking about functions of a single variable, it's not so surprising that you can do this. But the key observation is that getting this situation requires a delicate balance between these coefficients. The idea is that if you took any one of these coefficients, let's say you took a sub 100 and you wiggled it a very, very tiny amount, you would completely destroy the good behavior in the Reggie limit. Okay? So you're not allowed to randomly wiggle different coefficients. All the coefficients have to be related to each other in a very delicate way in order to get this to happen. So there's a beautiful way to express this delicate balance between the different coefficients. And that's provided by something called the Froissart-Gribov formula. In this case, it's very simple. So the idea for deriving the Froissart-Gribov formula is to start with an inversion formula for the a sub j coefficients. And this is just complex analysis. And I'm going to call this a Euclidean inversion formula. Because it involves an integral over a circle surrounding the origin. So it involves an integral over w of the form e to the I theta, i.e. it's an integral over imaginary boosts. Okay? And imaginary boosts are just rotations in Euclidean space. So that's why I'll call it a Euclidean inversion formula. And then the idea of the Froissart-Gribov formula is just to do a contour deformation in this integral. Okay? So we have a cut going from 1 to infinity. We start with an integral around the origin, and we blow up the contour and end up with an integral around the cut. We have an integral around the cut plus a contour at infinity. But we can drop the contour at infinity provided that j is large enough. Okay, so deforming the contour, you get a different expression for these a sub j's as an integral over the cut, so an integral from 1 to infinity, dw over w to the j plus 1 times the discontinuity of a, where the meaning of the discontinuity is that you evaluate a above and below the cut. Okay, this formula is valid provided j is large enough. And in this case, in order, based on the assumption that we made about the growth of a at infinity, the formula holds if j is bigger than 0. Okay, so for the partial wave coefficient a sub 0, you need to go back to the Euclidean formula. And that makes sense because the a sub 0 coefficient is not constrained by this boundedness in the Reggie limit, right? We can wiggle the a sub 0 coefficient and nothing changes. Okay, so that's why it's not captured by this formula, which I'll call a Lorentzian inversion formula. because it's an integral over real W, i.e. an integral over real boosts. Okay? So the remarkable thing about this formula, maybe it's not so remarkable since we're just doing complex analysis in one variable, is that the formula makes sense for general complex J. At least complex J satisfying this condition on their real parts. So the condition here is just that real part of J is bigger than 0. In particular, we can let J be, for example, any real number bigger than 0. And this formula works. The reason this formula works as opposed to this one is that we now have an integral over this cut, and 1 over W to the J plus 1 is a perfectly fine function along the cut. Whereas in this formula, if we tried to set J to be non-integer, we have a problem because the integrand now is not single valued as we go around the circle. Okay? So this thing is analytic in J. And that's very nice because this analyticity in J is a way of expressing the delicate balance between the A sub J coefficients. So not only is this formula analytic in J, but it has nice behaviors at infinity in the J plane. And it makes these partial wave coefficients, it makes the function, the analytic function that this defines, a kind of rigid structure. And it tells you that it automatically enforces this fact that when you wiggle one A coefficient, you have to wiggle all of the others at the same time. Okay, so analyticity in spin is a consequence, a necessary consequence of boundedness in the Regge limit. And as an exercise, if you like, you can do the fun example: A sub W is log of 1 minus W. So plug this into the inversion formula and check that the result agrees with the coefficients in the Taylor expansion of this function, just as a sanity check for yourself. Okay, so the situation that we're facing in conformal field theory is exactly analogous to this toy model. We have an expansion where each term in the expansion is growing, but we have a proof that the result is bounded in the Regge limit. And this implies analyticity in spin for CFT data. This analyticity in spin is beautifully expressed by Lorentzian inversion formula due to Karen Huo, which is directly analogous to this Lorentzian inversion formula we just derived. Okay, so let me write down Karen Huo's formula. So first of all, to write it, we need to start by packaging all the OPE coefficient information into one object. So I'm going to write the conformal block decomposition in a slightly different way, as a sum over spins and an integral over dimensions. It's going to be an integral over a complex contour running along the imaginary direction with a coefficient function C of delta J and then a conformable block. And there will be some extra terms that are not captured in this way of writing the expansion that I'll call non-normalizable terms. And one such term is the contribution of the unit operator. And these are essentially going to be a finite collection of conformal blocks with dimensions less than d over 2. When I say a few more words, it will be clear why we need to add those back in. So the idea is that this coefficient function should have poles at the locations of physical operators. So minus a sum of poles where the residues of the poles are squared OP coefficients and the positions of the poles are dimensions. If this coefficient function has this form, then this can be related to the usual conformable block decomposition. We have an integral over delta along this complex contour. So this is the delta plane. The coefficient function C of delta J has poles on the real axis at physical values. So, and another important fact is that the conformal block decays exponentially in the right half delta plane. One way to see that is that at large delta, the conformal block goes, well, it goes like rho bar to the delta over 2, where rho and rho bar are between 0 and 1. Let's say the absolute value of rho and rho bar between 0 and 1 when we're in the regime of OPE convergence. Okay? So as long as we stay within the regime of OPE convergence, this thing it dies exponentially in the right half delta plane. And so that means we can take the delta contour and deform it to the right and wrap around all the physical poles.
That is block plus the shadow.
Great, good. So for the sake of simplicity, I used shadow symmetry to remove the shadow term. Okay, I'm going to end up skipping over a whole bunch of technology in this discussion. I'm going to try to take a windy path through, so I'm not going to talk about the shadow term. But this is a valid way of writing the OP. Yes?
What if I have operators on the principal series?
Great, that's a great question. So the question was, what if you have operators on the principal series? And in that case, I believe the correct prescription is to use a principal value prescription for doing the integral. Okay. Good. So this coefficient function packages together all of the dynamical information in this 4-point function, and we would like to compute it. And Karen-Ho's formula is an interesting formula for the coefficient function that involves an integral over Lorentzian kinematics. So the statement is that C of delta J is, so first of all, it has this 1 plus minus 1 to the j, which enforces that it's non-zero only at even integer j. And that is good because we're studying here a 4-point function of identical operators, and identical operators contain only even spin operators in their OPE. Then there's some coefficient kappa over 8 that I'll write in a second. And then the interesting part is an integral over cross ratios. And it's an integral over a square in cross ratio space with some measure times a funny conformal block where dimension and spin have been swapped. And hopefully by now the swapping of dimension and spin doesn't scare you too much. So this is different from the swapping that you see in the light transform. But it's also an example of an affine Weyl reflection. Okay, so you can check for yourself, look at the formula for the conformal Casimirs, the quadratic and quartic Casimirs, and you can check that this swapping preserves the conformal Casimirs. And then this multiplies. Let me give myself a little bit more room. So still in the integrand, a function of cross ratios, and I'm going to write the function of cross ratios in terms of space-time coordinates because it makes the physical interpretation a little bit clearer. So it multiplies the 4-point function, but a double commutator. So this double commutator is just a linear combination of the different Whiteman orderings that we just discussed. In fact, maybe it's still here. Yeah, great. So this is just a linear combination of these 4 different terms. And these factors serve to make it a function of cross ratios alone. Okay? So multiplying by the dimensional factors, this thing is just a function of z. And if you want to see what it is, you just take a linear combination of these things. And so we can just use this formula here. And it's equal to g where we continue to the left, plus g where we continue z bar around 1 to the right, minus 2 times g. And I'll define this as minus 2 times the double discontinuity of g. Okay? And it's a function of cross ratios. And that's this whole thing. And this double commutator is supposed to be evaluated in kinematics where it's non-zero. And that's precisely the Reggie kinematics that we've been talking about. So specifically, the picture is that we have 3 and 2 being time-like from each other, 1 and 4 being time-like, and all other operators space-like separated. Okay, so this formula has some really beautiful properties. One important property is that the double discontinuity has some, it's often much simpler than the 4-point function itself. At least in so an example of a case where it's much simpler than the 4-point function itself is, let's say, in a theory with a large n expansion. One beautiful property of the double discontinuity is that at leading non-trivial order in the 1 over n expansion, double trace operators do not contribute. It gets a contribution purely from single trace operators. And that means that Karen-Ho's formula gives all of the data, in both single and double trace data, which is encoded in C of delta J, in terms of just single trace data. So it's a very efficient way to determine CFT data in terms of just a smaller part of the spectrum, the single trace part. And there are similar simplifications that happen in weakly coupled theories. So in weakly coupled theories, if you compute this double discontinuity, you'll find that it's much simpler than the full 4-point function. And yet that double discontinuity determines the full 4-point function through this formula. And the fact that d-disk is so simple is, I think, at the heart of a lot of recent advances in the analytic bootstrap. So there's been a lot of work recently on bootstrapping theories at large n, weakly coupled theories, bootstrapping strongly coupled holographic theories, where by bootstrapping I mean determining 4-point functions and CFT data in these theories at a few leading orders in, say, the 1 over n expansion. The thing that this formula provides for you is a relationship between the 4-point function and its discontinuity. And you should think of this as being kind of like a unitarity method in the context of amplitudes. So in amplitudes, we have methods for using the analyticity properties of amplitudes to relate the full amplitude to its discontinuities. And in that way, you can take smaller pieces and glue them together. So you can take lower point amplitudes and glue them together into higher point amplitudes, or lower point amplitudes and glue them together into higher loop amplitudes. And this formula gives a way of doing something analogous for CFT 4-point functions, at least at a couple of non-trivial orders in 1 over n. Okay? Unfortunately, we won't have time to discuss a lot of that, but I just want to mention that this idea of looking at the double discontinuity has really had central importance in a lot of recent bootstrap work. So the other remarkable thing about this formula is that it's analytic in J. And it's really the CFT analog of that formula that we wrote over there. And the analyticity in J, in the formula, you can see because it's an integral over this square in cross ratio space where the cross ratios are real, and the only place that J enters is in this conformal block. And J is sitting in the slot of the conformal block, usually reserved for delta. And it's a familiar fact that conformal blocks are analytic in delta. So of course, this thing is analytic in J. As a consequence, this formula works for any complex J. Actually, well, so it works for complex J, but there is a constraint on the real part of J, which is analogous to that constraint that we had over there, and it has to do with how bounded the 4-point function is in the Regge limit. And the Regge bound that we derived using the Cauchy-Schwarz inequality implies that this formula should work for J bigger than or equal to 1. So similarly to that previous case, if you want to know the CFT data for J equals 0, you have to do something else. Yes? Oh, great. So the non-normalizable contributions are not captured by the equation because they're scalar blocks. So that's part of this issue that I mentioned, that the equation only works for J bigger than a certain value. That's right, yeah. So at least in a unitary theory. So the non-normalizable contributions are the operators whose dimensions are less than d over 2 because they're not contained in this contour. And in particular, the unitarity bounds require that those are only scalars. Okay. Good. So it's analytic in J. That means that CFT data can be analytically continued in J. And that means that I should draw a plot a lot like the one that Juan drew earlier today of the CFT spectrum as a function of J and delta. And it's conventional to plot J versus delta minus d over 2. So the idea is that so there's some spectrum of local operators in the theory. So for example, here's the stress tensor. So this would be at d over 2, 2. Yeah. Yeah. So Simone derived it for arbitrary scalars with arbitrary different scalars, and in a paper with Peter, we derived a general version for arbitrary operators and arbitrary representations.
So, for example, if you take some simple theory, like a two-dimensionalizing model,
yeah.
and then analytically continue the data from different correlators, do we get that the analytic continuations agree with each other?
Can you repeat the question?
The question was, if you look at different correlators in the 2D Ising model, I think the question is jumping ahead a little bit. Maybe can I state the question after I draw the plot? Okay. So the idea is that there's some spectrum of local operators in the theory. So here's the stress tensor, and there's a unitarity bound that says that the local operators have to be to the right of this 45-degree line. So maybe the lightest spin 4 operator would be there, and then you could have spin 6 operator and so on. And there may be other spin 2 and spin 4 and spin 6 operators. These operators appear as poles in C of delta J, but C of delta J is analytic in J, and that means that we can draw curves through the operators. Now, one thing that I don't have time to explain is that C of delta J has a so-called shadow symmetry. Under delta goes to d minus delta. So the correct thing to do is to make this plot symmetric. And these points are so-called shadow points. They don't correspond to local operators, and I'll try to explain what they do correspond to in a second. Okay, so what I'm really plotting here is that this is a plot of the poles of C of delta J, and C of delta J is determined by applying this formula to some specific 4-point function. So one very natural thing that you could ask that I think is an open question in general is, if you apply the inversion formula to different 4-point functions, would the poles be in the same place? Okay? So we know that at integer j, all the poles will be in the same place because the same local operators participate in every 4-point function. Modulo conserved charges and so on, but let me talk about some fixed charge sector. Okay? So we know that at integer points, all these curves have to go through the same places. And Pedro's question was, if we look at different 4-point functions, are the curves in the same place at non-integer points? And one way you might test this, for example, is in an exactly solved theory like the 2D Ising model. You could plug in the 2D Ising model data and see where the curves go. And I think in that case, the answer is yes, they're in the same place. And part of the reason is that the Regge trajectories, so by the way, these curves are called Regge trajectories. Regge trajectories in the 2D Ising model are extremely simple. They're just lines. So straight lines. So the fact that they have to go through the same integer points guarantees that they'll be the same at non-integer values.
That's true for any minimal model?
I suspect it's true for any minimal model, but I haven't checked that. Yeah, this is an important question. And the question of whether the Regge trajectories are the same in any 4-point function directly relates to the stuff that I'm going to talk about next when we discuss light ray operators. Okay. Good. Okay, so these points on the plot are supposed to be local operators, but you could ask, what on earth do the other parts of the curve represent? What are they supposed to represent? In particular, so we can analytically continue CFT data in spin. What about the operators themselves? Can we analytically continue the operators themselves? So it's not hard to convince yourself that you can't analytically continue local operators in spin. Here's an argument. So for a local operator, sure.
Is the fact that they are very simple Regge trajectories, the fact just related to having Virasoro rather than
The question was, is the fact that they're very simple Regge trajectories related to having Virasoro? I think it's related to the absence of anomalous dimensions, which I think, yes. So I think it's related to the fact that the higher spin operators are determined by, their spectrum is determined by Virasoro symmetry, and they're beautifully equally spaced.
they are anomalous, right? 1/8 is very anomalous.
That's right. By anomalous, yes, that's true. Okay. Yes, I think it's related to Virasoro.
And is there an analytic continuation in the Virasoro sense, like sum over primers, and I analytically within the label?
So in general, the analytic continuation in spin is not always related to Virasoro. So I think it's a statement about minimal models. I'm guessing it's a statement about minimal models. And the reason is that, so these Regge trajectories, let's first talk about n equals 4 superior Mills theory. This trajectory is the trajectory of single trace operators, which are dual to spinning string states in the bulk. Now you can put a string theory in ADS3, and you'll have these same kind of GKP strings. And you expect those things to live on the same Regge trajectory, the single trace states. And that Regge trajectory will definitely have some non-trivial shape. So in a 2D CFT that's dual to a string theory, I would not expect the trajectories to be straight. Yeah?
Does the formula say something about like the directions out of the board and complex delta?
Absolutely. So the formula works for complex delta. Actually, strictly speaking, the best place where the formula lives is for delta on this principal series, on this contour, and then you have to start analytically continuing in delta to get to different places.
So what happens to those Regge trajectories?
Yeah, so this Regge trajectory looks kind of like a saddle point. So it has a saddle point here. If we go in the complex direction in delta, it goes down. At least that's true in n equals 4 superior Mills theory. I think it's expected to be true more generally. Okay, all right, so I was describing this argument that you cannot analytically continue local operators in spin. The argument is that a local operator does not kill the vacuum. That's the state operator correspondence. You act with a local operator on the vacuum, you get a non-trivial state. But if you had a continuous spin operator, so first of all, we know how to describe them using the formalism that I talked about yesterday. But I explained that a continuous spin operator has to kill the vacuum. Otherwise, it would create a state that violates unitarity bounds. And it's not possible to have an analytic function that's 0 at all non-integer values and non-zero at integer values. Okay? So we cannot analytically continue local operators. But we can continue their light transforms. So the light transforms of local operators evade this issue because they killed a vacuum, which we proved last time. And so what turns out to be correct is that this plot, which is called the Chu-Frauchi plot, so I'm going to really stick my neck out and try to spell it. Pedro, I don't know if you could do this one. This is
One of them is your calling.
yes, I know. Yeah, the hard one, the difficult one. This Chu-Frauchi plot is not a plot of the local operator spectrum. It's a plot of the light ray operator spectrum of the CFT. So we shouldn't have called this T. We should have called it L of T. And then this thing would be L of the next spin 4 operator. And the light ray operators of the theory, the light transforms of local operators, can be analytically continued to live on these Regge trajectories. This point of view, using this point of view in the very little time we have left, I even wrote those words in the notes because I anticipated this happening. We'll be able to give a proof of the Lorentzian inversion formula and also make contact with the causality-based proof of the average null energy condition. Now, I'm really not going to have time to do this very well, but I want to try to give you some of the highlights of how this works. The key step is just realizing what you're supposed to look at. You're supposed to look at this thing, and once you know you're supposed to look at that, you can kind of follow your nose and get led to this result. Unfortunately, you have to follow your nose using a bunch of technology that I won't have time to explain, but let me just show you how it works. So the rough idea is to start with something called a partial wave. And the partial wave is an integral of the 4-point function over Euclidean space. So this is the Euclidean 4-point function times a 3-point structure that picks out a particular operator. So if you integrate the 4-point function against a 3-point structure, so I'm going to use an omega subscript to represent a physical correlator. So this is an actual physical correlator. And a 3-point function without a subscript will be just the unique conformally invariant structure consistent with those operator representations. So hopefully Slava wrote a formula for the 3-point function of 2 scalars and a spin J operator. This is just that function. And it has the property that it gives you a formula for C of delta J. C of delta J, this thing is fixed by, oh, by the way, okay, so I have to explain some things. So the tilde means that these things have dimension d minus delta phi. And the reason for that is that phi tilde together with phi and a measure factor has dimension 0, and therefore you can integrate it in a conformally invariant way. Okay? So this is the unique thing that you can choose to make this integral conformally invariant, and the answer is therefore fixed by conformal symmetry to be a 3-point structure involving the things that have not been integrated. and the coefficient is C of delta j. So this is a Euclidean inversion formula for C of delta j, and it's analogous to that the starting point there, the contour integral that we started with. So this is a formula for C of delta j, but it does not work for non-integer j. Okay, so this object, another way of saying this is that this object, the partial wave, encodes in it all the matrix elements of operators appearing in the phi1, phi2 OPE, right? The residues of C of delta j are just the OPE data of those operators, and then this thing multiplies by the actual three-point structure associated with those operators. So we have the property that the residue, a residue at delta equals delta k of the partial wave is equal to some overall OP coefficient times an actual physical three-point function. And this is just a combination of this formula with that formula for the residues of C of delta j. Okay, so this partial wave encodes in it all of the data of the phi1, phi2 OPE, but we don't want to study the local operators in the phi1, phi2 OPE. We want to study their light transforms. So what we should do is take the formula and Wick rotate to Lorentzian signature, and then take the light transform. So when so we're going to take this formula and Wick rotate it, and Wick rotating means that we take all the times, all the Euclidean times, and continue them to e to the I pi over 2 times some Lorentzian time. So we take all the times and we rotate them simultaneously, including for the integration variables and the external variables. And if you Wick rotate a Euclidean correlator, you land on a Lorentzian time-ordered correlator. So we end up with exactly this formula, but now over Minkowski space, with the integrals over Minkowski space, and we have Lorentzian time-ordered correlators. And then the next thing we want to do is light transform it. And the light transform is going to hit this guy. So the thing we have to do is compute the light transform of a Lorentzian time-ordered correlator. Okay, where this light transform is hitting this guy. This is kind of a fun computation. So let me put the two operators 1 and 2 like this. So this time-ordered correlator can be written in terms of different Whiteman correlators depending on where O is. Okay. Now let's suppose. Let me draw the light cones of 1 and 2 because we'll need them in a second. Let's suppose that that O is down here and we do the light transform over this contour. Everywhere along the contour, O is either in the past of 1 and 2 or space-like from 1 and 2. And that means that inside this time-ordered correlator, we can put O on the right. But the light transform of O kills the vacuum. So this thing would give 0. Similarly, if we had, let's say O was here, and we did this light transform, so everywhere along this contour, O is either space-like from 1 and 2, or in the future of 1 and 2, and therefore we can always put O on the left, and then the light transform kills the vacuum. So the only way to get something non-zero is if O starts in the past of 1 and ends in the future of 2. And let me see if I can draw this. So here's Minkowski space. So we have this constraint when we do this thing, we're going to get a theta function that's constraining O to be in the past of 1 and end up in the future of 2. And another way of writing that is to draw the cousin of 2 in the other point gray patch. So this is 2 minus. And then the condition is that O is in the future of 2 minus and the past of 1. Okay, so this is going to give us some term with a theta function that says that x is in the past of 1 and the future of 2 minus. And the thing that it multiplies, if we're in this situation, everywhere along the contour, this time-ordered correlator is equal to a Whiteman correlator where 2 acts on the vacuum, then we have O, and then we have 1. So this thing multiplies the light transform of Whiteman correlator. And then there's a similar term with 1 and 2 swapped. Okay, so what we end up with is that the light transform of the partial wave is equal to an integral against this kind of thing. And in particular, this suggests that we should define the following object, which I'll call funny O of x and z. And this is an integral over these kinds of kinematics. So the theta functions will enforce this condition, an integral of x1 and x2 of the operator phi1, phi2 times this light transformed Whiteman function. And then plus 1 goes to 2. Okay, and so here's the magical thing that happens. These light transformed Whiteman functions make sense for non-integer j. So the original Euclidean 3-point functions don't make sense for non-integer j. And if you want, I can explain that during the break. But after you take the light transform, you get something that does make sense. And the analog here is this toy example that we had, where we had an integral over a unit circle, where it was important that w is an integer to get the integral to be single valued, versus an integral over a cut, where it wasn't important. Basically, the same thing happens here when you take the light transform, and it means that this object is actually analytic in J. And furthermore, by construction, it has the property that its residues at integer j are equal to light transforms of local operators. So this is when j is an integer. That's by construction. So it means that we can interpret the residues of this thing in delta as being analytic continuations in J of this thing. And that's exactly what these curves in the Chu-Frautschi plot are. Okay. I'm running out of time, or maybe I already have run out of time, so I'm not going to be able to give the argument, but you can look at it in the notes. If you study a matrix element of these things, so far the matrix element of these things, let's say phi 4, funny O, phi 3. This is an integral of this 3-point structure against time-ordered 4-point function. Okay, that's what comes from this expression after you Wick rotate it. But it turns out that you can do some contour manipulations. The contour manipulations are exactly the same ones that appeared in our proof that the light transform of a local operator kills the vacuum. They have to do with the regime of holomorphicity of the time-ordered 4-point function, and show that this is can be rewritten as an integral of the double commutator. So you can rewrite it as an integral of a double commutator against this light transformed 3-point function. And on the other hand, this thing was proportional to C of delta J. And after some massaging, this gives Karen-Ho's formula. Okay. The really important step is the contour manipulation where you pass to the double commutator, which unfortunately I don't have time to explain, but it's in the notes. And the other comment that I want to make is that having an expression for matrix elements of light ray operators in terms of a double commutator can be very powerful for understanding positivity conditions. And this has to do with Rindler positivity. So the idea is that if 1, 4 and 2, 3 are in a Rindler symmetric configuration, then you can think of this thing as in terms of our Rindler inner product. So this thing becomes the Rindler inner product of the commutator with itself, up to a minus sign. So this is the case if we're in this Rindler symmetric configuration where phi 1 bar is phi 2 and phi 4 bar is phi 3. So it means that in Rindler symmetric configurations, this double discontinuity, this double commutator is actually positive. And you can use that to, for example, prove the average null energy condition. So the Anak operator is equal to this funny O in the case where delta equals D and J equals 2. So you plug delta equals D and J equals 2 into this expression and use Rindler positivity to show that it's positive. That essentially recovers, it's a way of looking at the causality-based proof of the Anak due to Hartman et al. Okay, so I know things got super sketchy by the end, but I wanted to mention these two results because they tie together a lot of the things that we've been discussing. And so I'll stop there. Thanks. Do you have to, so the question was, do you have to worry about the discrete series in this case? And there's a theorem that says that the discrete series doesn't appear in it doesn't appear in the OPE decomposition of two scalars, or rather the harmonic analysis decomposition of two scalars. I'm actually not sure what the full story is with discrete states. But I think that one could start with the completeness. Okay, so one can start with the completeness relation for scalars that I'm implicitly using here and apply differential operators to get completeness relations for spinning operators. I'm not totally sure where discrete states would enter, but I just don't know the answer. But they don't matter in this case. Yes?
Did the proof of Rindler positivity depend on unitarity in the central way?
The question was, does the proof of Rindler positivity depend on unitarity in a central way? And the answer is yes.
Like if the operator dimensions don't satisfy the unitarity bounds, you can have, like there are lots of ways you can violate unitarity, of course.
Right, you're asking, does Rindler positivity hold in a theory where operator dimensions don't obey unitarity bounds? Yeah, I think not necessarily. Rindler positivity is closely connected to reflection positivity. So for example, in the case where you just have one operator on either side, it literally, you can put them both at time slice 0, and then it becomes a Euclidean correlator, and then it is reflection positivity. Yes?
Is it more structured to be studied in that function
So the question was, if you look at higher point functions, can you derive, can you see more structure or something like that?
Or